Good morning, everyone. First and foremost, thank you to Alejandro for inviting me to come to this conference. It's extremely exciting to be here, mostly because a lot of the ideas and things that are being presented here are, things that we were, thinking about drawing on a whiteboard when we were doing our project, and so it's wild to see a lot of this come to fruition. So the idea of using ultra-high temperature thermal energy storage and conversion in the spacecraft literature has actually been around since the 1950s. And the reason for this is that with these high temperatures, you have high quality heat, and if you have high quality heat, you can then generate a high temperature working fluid and use that for both propulsion and power. And so having this technology is enabling for what's known as a dual-use thermal bus. So the idea aboard a spacecraft is that you have a thermal bus capable of providing your electrical power needs and also your propulsive power needs. And so in this case, you have a thermal energy input that has been stored in high temperature PCM, which is then directly converted via thermoelectric conversion. Or you use that to transfer heat to a working fluid via heat exchanger, and then you have propulsion and then you have either propulsion power out, or you can also do high power dynamic conversion. So within the literature, there's sort of two compelling cases for this configuration. The first of these is solar thermal propulsion. So in the case of solar thermal propulsion, you're taking concentrated sunlight, heating a heat exchanger, and then you take cold propellant, blow that through the heat exchanger, and then eject it out of a nozzle. Solar thermal is interesting that it gives you both high efficiency, or relatively high efficiency, and also high thrust. The second case I'm going to talk about, which I think is a little more interesting, is a pulse radioisotope system. So in this case, you use a radioisotope thermal decay here, and you couple that then to a ultra-high temperature PCM. And what this allows you to do is take a very high specific energy source and then also generate high specific power. So first I'll talk about solar thermal propulsion. Solar thermal propulsion, despite the fact it's been under development for 60 years, has never actually flown. The reason for this is it has a complicated architecture. So the idea that you need to have the solar concentrators and also your traditional spacecraft systems. It's also considered to be very high risk, which is a little bit of a self-perpetuating cycle. The longer it doesn't fly, it never reaches that higher TRL level, and will always be this novel technology. Throughout its development, there's been multiple declarations of technological feasibility, so the concept is sound, and typically these programs actually get canceled via, I really got to speak into the mic, huh? Okay. So I'm used to, when I teach in a lecture hall, I usually don't use a mic because I can hear myself. Typically, this stuff gets canceled, not necessarily due to technological reasons, but it's to program and budget regions. It's high risk, and so very quickly solar thermal is down-selected away, so you can use something that has flight heritage with maybe a little bit less performance. And the reason this trade usually goes not in favor of solar thermal is solar thermal has scaling problems. And so if you're using a ammonia-based solar thermal rocket, you get about 400 seconds ISP. So the question is that enough to actually justify the risk when you can get into the 300s using a bipropellant system? Also on board large-scale spacecraft, what you end up with is the ability to have high-power EP, so you can have large photovoltaic arrays. You can also use relatively high-efficiency bipropellants. And then finally, one of the things that you deal with in solar thermal propulsion is one of the main benefits of solar thermal is your total transfer time. And so in this case, if you can allow your spacecraft mission to be longer, then you can use EP, which has flight heritage and can give you unparalleled efficiency at the cost of your total mission duration. So with these scaling problems and all these issues with solar thermal propulsion, it down selects in sort of a niche environment. And this is what we worked on in the HEATS program. So the High Energy Advanced Thermal Storage Program at the AFRL was motivated by the idea of a microsatellite, so a sub-100 kilogram satellite that required both high thrust and high delta V. And it was identified that a bimodal STP system would be a unique capability for this. So looking at the existing micropropulsion technologies, there wasn't anything that could give you a quick response time with an aggressive delta V budget. And so we targeted bimodal solar thermal propulsion, specifically using silicon and boron as phase change materials. So during this experimental effort, we did some solar furnace tests, and we melted some silicon, and we looked at some of the practical realities of how this operates. But what I'll talk about here is how is this technology actually applied, and then some of the concerns that you have to think about when you're sizing this for a spacecraft. So as we went through this development, we looked at all the technological requirements for a bimodal solar thermal system, and we found that the majority of these technological requirements were met. So solar concentrators, fiber optic power coupling, thermoelectric conversion, and advanced insulation, all of these things had viable technological pathways. In 2015, when we were working on this research, the developments at EdTech seemed to be the most interesting in thermal photovoltaic conversion, but the work with the Amadeus project has far surpassed that, and so that now is our new benchmark. And what this left is these two things. We have the high temperature storage material, so we want a phase change material that is applicable to spacecraft propulsion temperatures. It also has a high energy storage density. And then we also needed a compatible and effective receiver-absorber converter. So just because I have this energy storage density doesn't mean that I can effectively extract this into my system. So once again, the group, the Amadeus project, has pushed forward with the idea of this high temperature storage material, with the idea of using these alloys that eliminate some of the expansion problems. And so what that leaves to discuss is this effective receiver absorber converter. So how do we actually pull energy from our system? A good way for us to look at this is to compare the performance of an existing bimodal solar thermal system using sensible heat thermal energy storage to one where we apply a high temperature phase change material, and we can start to see what benefits are possible. To do this, what we'll focus on is the ISIS program. So this is the Integrated Solar Upper Stage program. So this was conducted in the mid-1990s, and they actually succeeded in performing ground tests of an integrated receiver-absorber converter. And so in this case, they had a graphite thermal energy storage mechanism with a blow-down heat exchanger for their solar thermal rocket, and they took advantage of thermionic converters, and they ground tested this and published their hydrogen hot flow results. And so in this case, we can use this as a baseline for what can you see in a sensible system, and we can then apply a phase change material to this system and see what happens. So in order to make this comparison, we did some basic 1D modeling. So we looked at the ISIS design, which was 195 heat exchanger passages, and consisted of about 15 kilograms of sensible heat thermal energy storage by means of graphite. And then there was also 10 kilograms of rhenium coating to protect that graphite in a hot hydrogen environment. So that was also incorporated into the thermal energy storage. And to model this, we simply took those 195 passages, or those material properties, divided them by 195 passages, and then did a simple axisymmetric model using the STAR CCM multiphysics package. So once again, to highlight what we're modeling, this is the central graphite annulus here. This was the thermal energy storage in the heat exchanger. We're basically just taking one of these representative passages and running it in a STAR CCM model. So if we use their exact same flow parameters and their exact same process for this axisymmetric model, the sensible heat behavior of the heat exchanger looks something like this. And so in this case, we see a typical sensible heat behavior where we have to reduce the temperature of our thermal energy storage medium to effectively pull energy out. But what's interesting about this is in their design, and this is also in their published data, you notice that in the first 150-ish, where'd we go? There we go. In the first 150-ish seconds, the exit temperature of the system actually remains relatively constant. So in the case of a thermal rocket, this is beneficial to maintain peak efficiency. And the reason this exists is because the effective convective coupling length they need, right? So the temperature, or the length required to reach thermal equilibrium with the propellant isn't the actual length of the heat exchanger itself. And so they're actually able to move this convective coupling region down the heat exchanger until you eventually start drawing heat from the entire assembly. And you begin to drop your exit temperature. So the first question that we can answer then is, what happens if I just drop latent heat thermal energy storage into this system? So we were looking at spacecraft systems, so we modeled this using boron. And if I apply a boron phase change material and a little bit of boron nitride to act as a container, I immediately get superlative performance. So the boron-based system, you see that your exit temperature maintains is stable. You see that your total delta V delivery, so the momentum you're able to give to your spacecraft, begins to increase as a function of time as we take advantage of this higher energy storage density material. And we see a better convective coupling environment because we have a relatively isothermal heat release. But what I want to point out for a spacecraft system is that this isn't necessarily helpful. And so what you're doing here is you have this much higher performance, but you're taking a huge technological leap because now you're incorporating this boron energy storage. And if your mission doesn't require burns beyond 200 seconds, your performance of your total delta V for a given amount of propellant ends up being exactly the same. And so the benefits that you're going to see from a phase change system in a spacecraft application are going to be mission dependent, right? And the other thing to point out is that these dependencies aren't actually that great. If I take these burns out to 1,000 seconds, I'm only gaining about 15% relative total delta V for a given amount of propellant. So what we could talk about then is the idea of an effective energy storage density. And so instead of looking at these materials just in terms of the material properties, we can think about it instead of how much energy can I actually extract from the system. In the spacecraft literature, both silicon and boron have been mentioned since the early 90s as phase change materials, but no one really ever did any experiments on them. And also they were always considered based on just the material properties by themselves. And so if we think about the effective energy storage density of this sensible heat system, we could see that, if your burns are allowed to go to about 1,000 seconds, you can get, a megajoule and a half of energy storage per kilogram. But in order for us to optimize for a phase change material, we have to pick something. There needs to be some mission or some target. So let's say that 1 megajoule per kilogram is enough. So we'll pick this as our starting location, and then we'll apply the boron phase change material based on this value. So to do this, what we did is we shrunk down the size of the heat exchanger. We added in some boron phase change material to hit this 1 megajoule per kilogram target. And what this did is it reduced the total mass and volume of the heat exchanger by 60% and 75% respectively. And if I run this model, what we can see is that for the initial stages of our burn, we have a relatively flat exit temperature, and then it begins to decay very rapidly, right? We've dramatically reduced the amount of sensible heat available, and so once we hit that target from the latent heat thermal energy storage media, this begins to decay. We can also see that in the relative momentum that I'm imparting to my spacecraft, up until that 500-second mark, we are a little bit better performance, about 2.5% better performance up until 500 seconds, and then we begin to decay. But we're able to actually then optimize for that condition, and based on this optimization, we can reduce the overall mass and volume of our system. One of the things that's interesting about this optimization is how do you actually effectively get heat from this latent heat media? So we mentioned earlier that the convective coupling length is actually only about a third of the total heat exchanger. So in this case, you need about a third of the heat exchanger to reach thermal equilibrium, provided you have a constant wall temperature. And so by optimizing, by keeping this length long and the diameter small, what you're doing is you're moving this effective convective coupling region further down the heat exchanger as time progresses and maintaining that exit temperature. This is also beneficial in the case of latent heat media because both silicon and boron have a very high or very low thermal conductivity right at their melting point. And so in this case, you're not relying on heat soak back through the heat exchanger. What you're relying on is simply moving that convective coupling process down the line as you exhaust that energy storage material. And so if we run both models at the same time, again, this illustrates the difference in this coupling profile. In the case of the sensible heat, you're moving energy back through the system. You have relatively shallow thermal gradients throughout, and this quickly degrades your convective coupling environment. Whereas in the phase change system, you have very steep thermal gradients that are caused by that high low thermal conductivity at the melting point. But because you're moving the convective coupling environment down that heat exchanger passage, you still maintain good performance. So what does this mean then for effective energy storage density? In the case of effective energy storage density, based on an optimization, we can actually get higher performance in sensible heat materials. And so it's a little bit less than the superlative numbers by just looking at material properties, but you can still get a 2 times, 3 times increase in your effective energy storage density if you optimize the system accordingly. For a spacecraft application, though, this isn't, again, necessarily that important. And the reason why is your specific impulse is tied to the square root of your temperature, and then the total delta V is directly correlated to your specific impulse. And so even in the case where we have this boron-based, very technologically advanced system, at the max here, you're still only gaining about 20% more delta V based on the simple sensible heat higher TRL level system. Similarly, if we do this optimization, you do see reductions in mass and volume, but again, we're not talking about 4x, 5x changes in your total, 4x, 5x changes in your total spacecraft capability. We're talking on the order of 10%, 20%. So to look at these mission-specific benefits, the HEATS program also looked at a sample mission. So we looked at a 100-kilogram microsatellite. In this case, we sized a silicon-based thermal energy, or dual-mode silicon-based system, and we targeted a 1,500 meter per second delta V. If you size all these metrics, you end up with a propulsion power mass fraction of 58%. If you maintain this exact same propulsion power mass fraction for a boron-based system, you get a little bit higher delta V, you get 850 meters per second, but that's because boron has higher energy storage density, so you have more mass on board for propellant, and you also operate at a slightly higher efficiency. And so this graph shows where these actually sit. So what we're trading here is we're trading our total delta V with the actual response time. So what time, or how much time does it take to deliver that delta V increment? And in this case, what you can see is that the solar thermal options sit in between chemical options and electrical options. So they offer this high thrust, high efficiency region, which is interesting, provided you care about your total response time. And so the first system, the silicon-based system, you get about 10% more delta V than chemical systems, and you still maintain a reasonable delta V. But in terms of spacecraft design, this isn't terribly compelling. You're not going to implement an entirely new architecture away from flight-proven hardware just for a 10% increase. Similarly, for a basic boron-based system, this is using existing weights and technologies. You get about 35% more delta V than a chemical system, which again, not necessarily worth it if you're thinking about implementing a new architecture. And then finally, this boron-based system, this assumes some improvements in energy density for the thermal photovoltaics, and it assumes some improvements in the fiber optic coupling. And out here, you actually start to get out of the reach of a chemical system. And so now, we can't accomplish this with chemical propulsion. You still have a response time that's measured in days. And this actually does end up being an enabling technology. In the case of a 100-kilogram satellite, you can now do things such as LEO to GEO transfer. But what I want to point out about this graph is that no matter what, all these missions can be accomplished with EP. All of them can be accomplished relatively easily with flight-proven hardware, the caveat being that this takes on the order of years, whereas now we're talking about days. And so this illustrates the idea with solar thermal propulsion and also these thermal rockets in general, is that you have to have that unique requirement for high thrust and high efficiency, otherwise this just doesn't trade. And so for that reason, I think an actually much more compelling application of the ultra-high temperature thermal energy storage and conversion for spacecraft is the idea of a pulse radioisotope system. And so this is actually proposed by the Center for Space Nuclear Research out of the United States Idaho National Laboratories. And what they propose is a system that gives you high specific energy and also high specific power. And so for the radioisotopes, they're considering plutonium-238. And so plutonium-238 has an extremely high energy storage density, right? It's 1.6 times 10 to the 6 megajoules per kilogram. So we're 1,000,000 times more dense than a lithium-ion battery. But the caveat to that is that this heat is released slowly. And so the heat release for this plutonium-238 is about 0.56 kilowatts per kilogram. And so you can't necessarily do a thermal rocket or a high-power application for that. But what if you coupled that source to then a high-temperature PCM? This now allows you to operate in a pulse mode and generate high power from this high-specific energy source. So first, I'll talk about the radioisotope thermal rocket. So the radioisotope thermal rocket, or rocket driven by a radioisotope source, has actually been explored in the 1960s. So TRW, GE, and Monsanto actually looked into this. And this is one of their designs. So this was the DART thruster, which was 1967. So this used a plutonium-238 fuel, which has an 89-year half-life. And this design was able to generate about 40 millinewtons of continuous thrust. And so the design here is actually relatively simple. You have the radioisotope source that's encapsulated here, and you flow propellant around as a heat exchanger, and then you inject it out a nozzle. So relatively simple design, simple construction, but relatively low thrust to mass. So TRW also looked at another design. So this is the Poodle thruster. It's also from 1967, and this used polonium-210 as the fuel. And so polonium-210 has a much shorter half-life, right? So this half-life is now on the order of days, and thus they were able to increase the heat release rate, and they were also able to increase your thrust by 2 orders of magnitude. And so again, in this design, we have that encapsulated thermal energy storage, we have flow passages, and it's ejected through a nozzle. But the design and trade-off between these two thrusters illustrates this issue with radioisotope systems. And so in a radioisotope system, you're trading this idea of power versus lifetime. And so no matter what, if you want to have high power density by the radioisotope source itself, you need to actually have a short half-life, which for a spacecraft system is extremely operationally complex. So imagine this Poodle thruster with its 138-day half-life. The minute that radioisotope source comes out of the reactor, it starts to lose energy. So that gives me a 138-day window to manufacture my thruster, get it to launch, put it in space, and then use it before before its performance starts to degrade dramatically. And so for this reason, these radioisotope thermal rockets are typically considering things like plutonium-238 and also americium. So in the early 2010s, the Center for Space Nuclear Research had the idea of coupling one of these radioisotope thermal rockets to a thermal energy storage medium. So the idea was a Mars hopper. And so this actually used sensible heat thermal energy storage based on beryllium, but the idea was you would have a plutonium-238 core, and this would then heat up this beryllium heat exchanger, and you use that to do blow-down firings of in-situ generated propellant. And what this would give you is a Martian rover that could do these 10-kilometer hops every time it charged and discharged in 2 to 4 days. And so you have a rover now with thousands of kilometers of total range, which is orders of magnitude beyond what we currently achieve with our current wheeled rovers. So this concept was then further explored, this idea of a pulse thermal rocket, in another program that they did with the NASA Innovative Advanced Concepts Group. And so what they looked at was a propulsion power module that could take a CubeSat-sized payload and bring it on interstellar missions. And so the reason this program is interesting is this actually did consider the idea of silicon-based latent heat thermal energy storage. Typically, there was about 30 megajoules in the system. The design here was a sample mission to the moon and Enceladus. And it incorporated a RTR that was capable of 3.2 kilometers per second delta V with a mixture of hydrogen and xenon propellant, depending on their efficiency and thrust needs. For this propulsion system, they demonstrated that you could get your Earth escape for, down to about 120 days versus 2 years for EP. But this is not the interesting part of the design, because again, if you can wait 2 years, then we don't have to deal with all this unproven technology and we can just launch with electric propulsion. The interesting part of their design was the fact that their thermal energy storage system was actually sized by the communication power requirements. So they have this small 6U CubeSat that has their scientific payload based on conventional spacecraft sizing metrics. A 6U payload would have access to about 15 watts, and so when you're out at that interplanetary distance, you end up with a very small communication window, and you also need high power for a meaningful data rate. And so during their study, they said that you needed about 25 kilowatts for effective communications at a megabit per second for their 6-minute communication window. And so what they sized is they sized a 25 kilowatt closed Brayton system that would use the hot core that was charged by the radioisotope decay, and then they would blow down a xenon working fluid through a Brayton turbine or a Brayton cycle turbine and generate this power when they needed it. So high pulse power when it was required. Also an interesting thing to note about the design was they included some sensible heat thermal energy storage into the absorber. The reason for this is to get rid of that waste heat in space, you have to radiate it to the environment, which is not very efficient. And so this way you could take all that waste heat, trap it in that sensible heat thermal energy storage, and then slowly release it while you're waiting for your next cycle. So the radioisotope systems are very interesting, but there are some major concerns. One is that radioisotope power doesn't meet the current paradigm of low-cost, small spacecraft. The reason why is these radioisotope materials are very expensive. So plutonium-238, if you can get it, is $4 to $8 million per kilogram if it's available. And the reason I say if it's available, being a big if, is that the U.S. production rate is currently ramping back up to actually manufacture about 1.5 kilograms of this material per year. However, that scale is set by the current rate of NASA flagship missions, which use this material for their radioisotope thermal generators. And so even if this material is available, you might not be able to get it because it's likely already spoken for. So in terms of spacecraft, what's interesting for the future? The most interesting thing in spacecraft for the future is that for any of these systems, you have to understand how you're coupling this working fluid to your heat exchanger for these blow-down processes, either for propulsion or for power. And so if we understand that convective coupling in the heat exchanger, we can then think about what is the effective energy storage density we're going to get from our system and actually trade it against mission performance parameters. Right? The only way that any of this is going to go to space is if it effectively trades with actually pretty superlative numbers against existing technology, and we can't begin to understand it unless we understand this blowdown process. One of the things I think could be interesting is that there's some potential for a modeling effort or an experimental effort to create either an empirical relation, maybe even like a non-dimensional relationship that allows you as a designer to look at top-line numbers for this convective coupling and effectively size your system. And so finally, in conclusion, most compelling application for this ultra-high temperature processes in space is likely this idea of having high specific energy source and generating high specific power in a pulsed mode. The caution is that it pays to be pessimistic in terms of spacecraft applications because a substantial risk to your system requires a substantial benefit. But in this case, there's some enabling scenarios where you need this technology, especially this idea of this pulsed power for communications. And something I also want to point out is that in the development of this technology, there's also things in the future that might actually drive your mission for a thermal system that isn't related to propulsion and power that then we can take advantage of. So an example is the spacecraft here. This is the Trans-Astra Mini-B. So this was recently awarded in the NIAC Phase 3, so this is the inaugural round of these awarded by NASA. And what this spacecraft does is it uses concentrated solar energy to optically mine an asteroid. And so their spacecraft design considers the solar concentrators for this optical mining. It also has a solar thermal rocket because you have the solar concentration system available. And so in this case, incorporating high temperature latent heat thermal energy storage to the spacecraft could definitely enhance performance, create a thermal bus, but most importantly, it wouldn't be what's driving the spacecraft mission, right? So it's something that because you already have this on board, you can then take advantage of. And with that, I'll open it up to questions.
Thank you very much for a very nice presentation, a perfect timing. So now we have time for discussion, so please don't hesitate to ask some questions.
heat transfer analysis that you showed with the thermal convection length, actually it's very similar to what we get in packed bed storage that is used in solar thermal systems for storing sensible heat rather than phase change heat. But the effect is the same. So, and in these systems where you have a packed bed and you have the same kind of thermocline, you can actually control the width of the thermocline and the rate that it degrades by changing the parameters for heat transfer, like the channel size and things like that. So it seems that also in your system, if you change diameters of the tube or affect the convection coefficient on the surface of the tube, you have a lot more flexibility than what you've shown here.
Absolutely. And the thermal models that are in here are actually the tail end of this project. And so within the spacecraft literature in the world that we occupied during that HEATS program, no one mentioned anything about it at all. And so one of the interesting things is the ability to do that tailoring and to see what are those parameters at these temperature levels, especially in the case of a thermal rocket or one of these high power blowdown systems where you want as much coupling as possible in as short a time as possible.
Thank you for a very nice presentation. When it comes to it seems like most of the work was on modeling. Did you also do any experimental work on boron and silicon? I saw, but on the boron part, because that was very interesting.
So actually, the HEATS program, this program that we actually did, the funding was cut about halfway through this program. And so we were set up to do a lot of experiments, and the modeling came after I ran out of money. And so initially what we ended up doing was keep going back. We actually, the first part of this project was actually building up a solar furnace facility to actually do these tests, and we actually ordered some thermal photovoltaics from Boeing, and we had a plan to do all these things, and we switched to that modeling after that funding sort of disappeared. And so in terms of the experimental effort, what we ended up doing was we succeeded in generating molten silicon in our crucibles using a solar furnace, and we did some basic modeling to show that you could use the temperature transforming method to do engineering level models of these phase change systems without having to worry about the movement of the phase change medium and void formation, etc. So we did accomplish some things experimentally, but definitely not as much as we would have liked to. Also, if anyone out there is thinking of building a solar furnace to do this research, don't use any other controllable heat source you can, because this also ate up a lot of time.
Thank you.
Thank you for this excellent work. It was really interesting with this application. I would like to give a comment. You do a modeling with that you take into account convection, right? More convection.
Correct.
But do you take into account radiation, or by neglecting radiation, do you think it's not so important, or it should be further, let's say, developed in the future? Because indeed, in the literature for such high temperatures, you cannot find many works that take into account radiation. So what is your comment on that?
So the comment, it depends on your time scale. And so in the case of let me pull this up. In the case of the ISIS system, what they did is they had their insulation scheme, it was multifoil insulation, etc. But they found that over the course of a discharge of the system, only about 15% of the total energy stored was lost through radiation losses. And so depending on your time scale for when you're charging and discharging, you can neglect that if it falls below a certain threshold. And so for our modeling, we considered it was effectively adiabatic, with the idea that with an effective radiation or effective shielding system, you'd maybe lose 10% or so of your total stored energy. In a terrestrial application or an application where you need to store this energy for a long time, it becomes a lot more important. But in our case, because our time scales are short for these thermal rocket burns, it was neglected.
And you have more, you have as well, let's say in silicon, you have inside the PCM maybe some, but okay, you can neglect that, let's say, because you have a different time scale, so you can neglect, because inside the PCM as well, you will have some,
You do, yeah. So not only that, but there's also the convective heat transfer within the PCM as it moves around. And so one of the things that we did was we looked at that. I did a simple MATLAB model using the transforming method for our system, and we showed that, within plus or minus 20%, you can model the thermal performance at what you actually care about, which in our case was a sense thermocouple in the rear of the system. And you could model that without taking into account that convective motion or these other heat transfer media, because the phase change material is encapsulated. And so our encapsulation scheme was this graphite crucible that worked as a reasonably effective heat spreader as well. And so we sort of, we did the experiment and the model to see how close they would be, with the thought that, well, if they're not close at all, now we have to refine our model to incorporate these. But they came out reasonably close, or at least enough for engineering models that we cared about.
Yeah, okay, great. Thank you.
Hi, thanks very much. I was just wondering if you could apply this to civil aviation at all, if you had any thoughts about that.
Perhaps. I know civil aviation is having this moment of, are we going to do electric aircraft and how we're going to store that? And it really comes down to power density. And so these systems are very high energy storage, but in this case you have to extract it. And so the work on thermal photovoltaics and what the maximum kilowatts per kilogram of that sort of system, I think, would really define that as a viable application.
Okay, so
All right. Thank you.